discussion, we shall be talking about some of the sensors that we can use for interfacing and for building some embedded system applications in this lecture. So, this lecture is titled, to continue with the previous one, Output Devices, Sensor and Actuators, the second part. So, here we shall be very briefly talking about some of the sensors like speaker, temperature sensor LM35, light dependent resistor, microphone, which we shall be showing as part of the demonstration. We shall not be going into detail, but very brief working principle, so that you actually understand how the thing is working. Okay. First, let us talk about a speaker. Well, you all know what a speaker is. A speaker is a device through which we can generate some sound, we can get an audio output, right. Now, a speaker essentially we call it as an electroacoustic transducer, which means it converts an electrical audio signal into a corresponding sound. That means, you give an electrical signal, a waveform as the input, and the speaker will generate a sound as the output. You can hear with your ear. Okay. Now, what is there inside a speaker? Now, inside a speaker, there is a permanent magnet and there is a movable electromagnet. Well, what is an electromagnet? Electromagnet is constructed out of some ferromagnetic material with a coil around it. Whenever there is a current flowing through the coil, that material becomes a magnet. So, the idea is like this: there is a permanent magnet and the coil around the ferromagnet is movable. Whenever there is a current flowing, this will become a magnet. So, it will either be attracted towards the permanent magnet or it will be repelled from the permanent magnet. Depending on the kind of current you are passing, there will be a vibration. Okay. This is the basic idea. So, when current flows through the coil of the electromagnet, due to the magnetic field produced, this material becomes a magnet and the two magnets either attract each other or there will be a repulsive force, they will move away from each other. This will happen depending on the polarity of the current, which direction the current is flowing. Okay. So, just looking into the diagram, just you see I have shown a diagram here. Here the permanent magnet is shown in the back, this is the permanent magnet, and in the coil is wound around a middle point. This can be connected or attached to the permanent magnet, or this can be a separate movable part also. There can be two different kinds of speakers you can manufacture. And when there is a current flowing, depending on the input voltage signal, there will be some current flowing in the coil. So, this coil will be moving forward and backward depending on the attractive or repulsive force, and there is a thin diaphragm connected to that coil. In a speaker, you must have seen there is a diaphragm like this on top, a thin soft material that also starts moving back and forward. There is a vibration. Now, if that vibration is in a frequency range that our ear can hear, we will be hearing a sound. Now, you know that the typical audio range is 20 hertz to 20 kilohertz. So, human ear is able to hear between this frequency range. So, if there is a frequency with which the diaphragm is vibrating in this range, we will be able to hear that sound, right. This is how it works. So, you see here you mentioned this electromagnet, you can see here, it experiences attractive and repulsive forces depending on the direction of current that is flowing through it. So, the electromagnet as well as the diaphragm will be moving up and down, there will be a vibration, and the frequency of vibration will generate a sound. Well, in most audio systems we also have a good amplifier circuit with very low noise, so that we get a very clear and nice sound. In all our music systems and other audio systems, we have a very sophisticated amplifier which is connected through this to connect to the speaker, so that you get a very clear sound, right. Okay. So, next let us talk about one kind of temperature sensor. This is a very popular temperature sensor which many of us use in our experiments. This is called LM35. Okay. This LM35 is a very convenient kind of a temperature sensor. It looks like this. You look at this diagram. There are 3 pins. Pin number 1 and pin number 3 are the power supply pins. Pin number 3 you connect to ground, and pin number 1 you can connect a positive power supply depending on the type number of LM35. This power supply voltage can vary between 4 and 20 volts. And the middle point, pin number 2, will be generating some analog voltage which will be proportional to the external ambient temperature. There are 2 versions of LM35 available. Some of them can directly generate a voltage proportional to the temperature in degree centigrade or Celsius. There is another version which can also give in degree Fahrenheit. Okay. So, some of the notable thing is that, as I had said, the output voltage is proportional to the temperature in these sensors. The kind of sensor that we shall be showing you, it will be proportional to the degree centigrade of the temperature. And this has all the circuitry built inside it. You do not need any kind of external calibration to be made, very convenient to use, and it has an accuracy of plus minus 0.25 degree centigrade, which is often sufficient in most applications. Okay. And it also consumes very low power, 60 microampere current during its operation. So, it is also a very low power device, very convenient. It can operate over a wide range of temperatures, minus 55 to 150 degrees Celsius typically, and of course, as I told you, the power supply range is also 4 to 20 volts. The other point to note is that the middle point is generating an analog output voltage, I told you, and it is proportional. So, what is the constant of proportionality? The constant of proportionality is such that there will be an increase in 10 millivolts in the output voltage for every degree centigrade rise in the temperature. This is how this device has been built. So, internally, I am not going into the detailed explanation. Internally, this device looks like this. You see, there are 2 transistors, some diodes, there are some amplifiers, there is a constant current source, and these 2 transistors are very peculiar. One of them has an emitter which is 10 times larger than the other. You see, I am not trying to explain how this circuit works, but the idea is that the currents that are flowing through the transistors, there is a strong dependence on the ambient temperature. That is how the temperature sensing is done, and the difference in the current that is flowing into these 2 transistors, that is amplified, and the voltage across this resistance R1, this is actually becoming proportional to the absolute temperature. And on the other side, this absolute temperature value, this voltage is through some other circuitry, the other amplifier is being converted into a voltage which can be made proportional to either degree Fahrenheit or degree centigrade. Both kinds of amplifiers can be designed. So, there are 2 families of LM35 devices I told you. One gives you the output voltage proportional to degree centigrade, other proportional to degree Fahrenheit. So, inside this circuit is like this. Okay. but to use it, it is extremely simple. Well, here I am showing a diagram where with an Arduino Uno board we are trying to connect. You see, this is your LM35, now which you have put on a breadboard. These vertical lines are all connected. Okay. Now, the leftmost terminal we are connecting into 5 volts. This is the terminal which is generating 5 volts. We are connecting it directly to 5 volts. The rightmost wire, this black one, this is connected to ground. You see, this is the ground terminal. This is connected to ground, and the middle one, which is supposed to generate the sensed analog output proportional to the temperature, this is connected to one of the port lines. You see, we have connected to one of the analog inputs, because it is an analog voltage. You can read the value of the analog voltage through an AD converter, built in AD converter. You can read the data and you can make a calculation what is the actual temperature outside, right. Okay. Now, let us talk about a sensor called light dependent resistor, which can sense light. Now, LDR is a very small device. So, it looks like this. It is a 2 terminal device and there is a transparent window on top. You can see some this kind of zigzag pattern inside it. This is how an LDR looks. It is very small in size. This LDR is sometimes also called a photoresistor. It is a resistance whose resistance value changes depending on the light that is being incident on it. This is how LDR works. Depending on how much light is being incident, the value of the resistance changes. So, you can measure the resistance, that will give you an idea about what is the intensity of light that is falling on it. Okay. So, internally it is made out of some semiconductor material, because semiconductor materials have this kind of photoresistive property. When light falls on them, their resistivity changes. Okay. So, here some explanation is given. When light or photons fall on the device, the electrons inside the device, they move from one state to the other. Typically, they are called valence bond, they move to the conduction band. Valence band to conduction band, if they move, that means the electrons become more mobile, resulting in a reduction in resistance, because flow of electrons result in a flow of current, right. So, more mobile the electrons are, higher will be the current, lower will be the resistance. This is how roughly an LDR works. And the other property is that as the illumination increases, the intensity of light, well, the unit of illumination is lux, you may be knowing. So, as the illumination increases, the resistance decreases exponentially. So, one point to notice that you see, unlike LM35, this is not a linear device. The resistance is not proportional to the intensity level, it follows this kind of exponential curve. And the other point to note is that the difference can be quite significant. You see, in this typical curve, here we have a resistance of the order of mega ohms, and on this point we have a resistance of the order of hundreds of ohms. So, from mega ohm to hundreds of ohms is a huge difference. So, if you have a proper circuitry to sense this change in resistance, you can very faithfully and accurately sense the level of light intensity. Okay. And the other point to note is that these devices are not lightning fast, it takes a little time for them to generate the output. Like when light falls on these devices, it typically takes of the order of tens of milliseconds for the device to respond and the output to settle down. And when light is withdrawn, again you put it in a dark place, then it can take a couple of seconds also, much longer time for the resistance to again go back to that high resistance state. Okay. So, this you should remember, that means the response time is not of the order of microseconds or very lower milliseconds like that, it can take a little time, all right. Fine. Now, talking about interfacing, well, interfacing very typically we use some kind of a resistance divider circuit. Like we can use an LDR, we can use a resistance R1 with a 5 volt supply, let us say, and this we can feed it to one of the analog input pins of our microcontroller, either Arduino or STM32. So, here this voltage output, what will be the value? It will be this R1 divided by R1 plus resistance of the LDR multiplied by 5 volts. This will be the value of this output voltage. So, you will have to first find out the range of analog output voltage in the expected environment. Let us see, you may be using the LDR to check whether the light intensity has fallen below a threshold. So, you will have to do an experiment and find out what are the resistance values in the dark state and in the light state. So, this R LDR, this value is changing. So, accordingly you will have to choose the value of R1, so that the change in the voltage output can be significant. So, that you can read this analog input in the microcontroller and take a decision what to do with that, right. Okay. Now, the last kind of sensor that we shall be talking about in this lecture is a microphone. Microphone, you all know, is something where you speak. Well, in our mobile phone there is a microphone. When we give a talk or a presentation, we have a microphone. Sometimes I also have a microphone connected in my collar here. I am speaking to you, you are able to hear. This is also a kind of sensor, a sound sensor. Some sound is being generated, that is captured by the microphone, and it is stored somewhere in electronic format. Okay. So, essentially what is a microphone? In terms of functionality, well, internally the arrangement is very similar to that of a speaker, but it works in exactly the opposite mode. A speaker converts an electrical signal to sound, microphone converts sound into electrical signals. Design is very simple, similar. There here also there is a diaphragm, but microphones are much smaller than a speaker. Typically speakers are large, you have also seen very large speakers. The sound boxes you have seen, the speakers are pretty large. But in contrast, microphone, there are microphones inside your mobile phones also, they are very small in size. There is a very small diaphragm inside. So, when you speak on it, the diaphragm vibrates. There is also a coil around that diaphragm, around that permanent magnet. Now, you are not passing a current through the coil, rather you are allowing the diaphragm to vibrate in response to the sound. Now, as the coil vibrates inside a magnetic medium, a voltage will be induced in the coil and you can measure that voltage. It is reverse, from sound you are generating an electric voltage, and that voltage will give a measure of the vibration that is being carried out in the diaphragm in response to the sound. Okay. So, this is actually how it works. The diaphragm moves back and forth, the coil which is attached to the diaphragm will also move back and forth. Just like a speaker, there is a permanent magnet, there will be a magnetic field in which the coil is sitting. So, as the coil moves, an electric current will be flowing through it because of a voltage that will get induced. So, sound energy gets converted into electric energy or electricity. This is how a microphone works. So, inside you see the smallest microphone can be very small, and here I am showing the basic microphone of a typical those bar kind of microphone you use while giving some lectures or some presentations. This kind of microphones are also used, and inside, as I told you, there is still a permanent magnet and there is a coil which moves, and as it moves there is a signal which is generated. Now, in speaker it was reverse, I was applying a current and because of that the coil was moving, the diaphragm was moving, but now because of the sound I am giving in front, the diaphragm is moving first, a voltage is being generated, that is my signal, right. This is how it works. Now, interfacing is also not quite difficult. I am showing a typical interface, there can be simpler ways of doing it also. You see here, this is the symbolic diagram of a microphone. Here I am showing you a transistor level amplifier which consists of some resistances and some capacitances. Actually, so whenever you are speaking, that is being converted into a voltage which is in the 0 to 5 volts level, in that range. So, here the typical interface is shown, where here you can see the microphone sitting here and the other circuitry you can see here, this is your transistor, right, and you have made the connection with this Arduino Uno. This is how you can connect it, but you see, let me also tell you, when you want to buy a microphone of this type for some experiments, you will find often that there are some products available which already have this circuitry built into it. So, if you buy it, you need not have to construct this circuit, directly this unit will give you a voltage that will be proportional to the sound you are making. You can connect it directly to the analog input port, like here it had connected to an analog input port here. So, you can connect it directly to the analog input port. Okay. So, with this we come to the end of this lecture. In the next lecture we shall be continuing with some more of these devices that we will be using to show you or demonstrate the interfacing experiments. Thank you.